Hello everyone and welcome. My name is IWOCL and I am the lead functional safety practitioner at CodePlay and have been involved in automotive safety work for the last 6 years. This presentation is a high-level introduction to Part 6 of the Automotive Functional Safety Standard ISO 26262, the requirements for software development. I will introduce in this talk to you the main principles the standard is trying to get across to designers of electrical systems in a vehicle. With that, I will highlight what I think are some of the requirements that can present challenges to the Kronos specifications, approaches to testing, and the SYCL and OpenCL integrations and design concepts. My aim in this talk is also to show you as practicing SYCL and OpenCL practitioners where the SYCL stack holds up pretty well to the requirements of the standard. And this safety related topic has so many facets, way more than can be covered in this presentation. Now, I will only cover the SYCL stack as a complete system and how the SYCL and OpenCL components support safety, not specifically the runtime implementation details, as these can, as you can imagine, be approached in many ways. Happy to have that conversation with you at another opportunity. Now, the automotive industry is very interested in open standards and what it can offer. The image of how well SYCL and OpenCL is ready for safety applications is still being formed. So let's make it a good one. First up is the history of the autonomous vehicle. I hope you find this interesting. I certainly did. And I thought autonomous vehicles were a recent technology, but evidently not. From the very first vehicles, people have been looking at ways to automate movements of goods and people. And surprisingly, we start this journey off in the 15th century with Leonardo da Vinci and his car. Many see this as a distant precursor to the car. This device is sometimes considered the world's first robotic vehicle. Now, there's a lot here in this part of the presentation, so I'm going to fast forward to 1977, where software was first being introduced into vehicles to control them. Over in Japan, a mechanical engineering lab pioneered the first computerized driverless car, which achieved speeds up to 20 miles per hour by tracking white street markers with machine vision. Later, 1987, which is seen as an important year, a German engineer named Ernst Dickmanns equipped his van with a bank of cameras and 60 microprocessing modules to detect objects on the road using cameras. It drove for hundreds of miles autonomously, a tremendous feat, especially with the computing power of the time. In 1995, General Atomics launched the Predator. We all know what that can do. Things started getting serious in 2002 when DARPA joined in and announced their first grand challenge. It offered a $1 million prize to the first autonomous vehicle that was able to navigate a 142-mile course through the Mojave Desert, and that continued until 2014. Meanwhile, back in 2003, Toyota produced the first ADAS system in a commercial car, and that was the automatic parallel parking system. Google launched its self-driving car project in 2009 in some secrecy, and by 2013 many of the other companies like General Motors, Ford, Mercedes-Benz and BMW were working on their own self-driving technologies. 2015 Tesla rolled out with their autopilot. Moving along to 2018, Nvidia revealed at the CES conference their new SoC for self-driving called Xavier, and that was the first to incorporate support for artificial intelligence. In 2020 Google's project was renamed Waymo, and by then Google had clocked up an impressive 300,000 miles of autonomous driving. Today, the industry is investing heavily with new players always joining the field. It is becoming a multi-billion-dollar industry with prospects of flying cars or even passenger drones. Now, to add some context to this history timeline, let's drop in when the C and C++ languages appeared. Now drop in when OpenCL and SYCL made their appearance. And now I'll drop into the timeline the automotive safety standards that were beginning to emerge to address the concerns about software in vehicles as it was becoming more prolific from the 1980s onwards. Now, as you can see here, the safety standards are introduced many years after the use of technology was first being used, and it is seen by some that the functional safety standards, because it lags the technology curve, stifles the progress of using complex software systems in vehicles. But there is a good reason why these safety standards were developed by the automotive industry. They were there to ensure high quality engineering practices, the designs work as intended, and above all safe. Let me show you. Here are the incident reports registered to the United States Department of Transport Agency, the National Highway Traffic Safety Administration, since 1996. And note, this is only for the United States, and this is only for reported incidents of software faults. As you can see, the faults grow as the cars use more software to control their systems. By 2016, the amount of lightning strikes shown here were so numerous they were too tedious for me to draw, but I think you get the idea. The automotive industry knew they had to do something to stop legislation forcing them into doing something they did not like. So what did the industry do about it? Well, they created a safety standard tailored to their industry. In 2011, they published the ISO 26262 standard, and it was adopted immediately by the European automotive OEMs, which is not surprising as the standard was developed by the Europeans. From there, it gradually got adopted by more OEMs around the world. Today, most of the OEMs follow the ISO 26262 standard, and not necessarily because of legislation requirements, but as a proactive means of establishing a reputation for safety for their brands. An unsafe reputation damages sales. Some of you may have noticed the notable exception to following ISO 26262 is Tesla, which has its own methodology for better or for worse. And this is not to say that ISO 26262 is perfect. It is recognized by the industry it falls short in many ways, especially when it comes to tackling the issue of AI in cars and enabling autonomous driving. Hence, there are new automotive standards that have appeared in more recent years to support safety in this regard. A good example is the supporting automotive standard Safety of the Intended Function, or SOTIF for short. This particular standard tries to provide mechanisms that gives assurances why complex systems like those used for AI in automotive vehicles are safe. Now I'll move on a little bit into what is ISO 26262. ISO 26262's objective is really quite simple. It is the management of faults that could occur in an automotive electrical system, and that is it. It's there for the reduction of faults, which in turn reduces the risks of injury to any vehicle occupants and people in the vehicle's vicinity. It fully understands that not all faults or risk of faults occurring can be eliminated, but it does ask that designers explore their systems and root out bugs as best as they can. It also asks designers to develop systems in such a way that where known risks or faults can occur, the system is able to cope and operate it in a deterministic manner on that fault occurring, and hence remove or reduce the chance of injury. Once that has been done, there are requirements to validate the system with the supporting safety mechanisms to show it does work in those use cases. The standard's aim is to remove potential hazards caused by the following types of faults: random faults and systematic faults. A random fault can be anything: a cosmic ray causing a bit flip in the memory chip of a control system. The second kind of fault is a systematic fault. More specifically, root out latent bugs which could cause a hazard to manifest itself in the future on a trigger event. Now, if you have written software for any length of time, you know a bug can manifest itself in many ways. And there, ISO 26262 is asking you to show evidence of a robust development environment which minimizes the introduction of bugs or non-conformities. So, how does ISO 26262 achieve this? Well, it goes about ensuring systems are safe and fit for purpose, and this is based on a set of principles. The first principle is to have a quality management system in place, like ISO 9001. The V-system development model shown here is from ISO 26262. The two colours in the V model represent what you would do on a day-to-day basis as part of your quality management. You start with the clearly defined requirements on the top left and move through all the stages to finally produce a product on the top right. A development environment with a quality management system ensures that everything is recorded to show the history of development and progress, and that your product meets the defined requirements. ISO 26262 adds more stages to this V model for safety analysis of the design and to ensure that the verification measures for a product meet not only its technical requirements, but importantly, the safety requirements. The V model represents the development stages of the whole system and for individual components in that system. And so, a SYCL application could be a component in a bigger system. Now, ISO 26262 is about the management of risk. It's there to reduce hazardous events arising caused by failures in a system. It wants all the system's functions to be deterministic in every way, and so it wants designers to show evidence that they thoroughly understand the behavior of a system in every way, and that includes when any faults occur. Now, the automotive industry and standard based risk of a system and criticality of a system using ACEL classifications, and these are specified by the OEM. ACEL is an acronym for Automotive Safety Integrity Level. There are 4 classifications ranging from A to D, D indicating the most critical. An ACEL is an indication of the criticality of the system to control a vehicle on a fault occurring and not causing injury to people. Let us take one of these systems and quickly go through how the ACEL rating is obtained. Using the vehicle's ABS brake system as an example, you first identify the hazard that could occur should the system fail. Next, think of all the situations when and how that hazard could occur. Then, you estimate how often that hazard or fault could occur during the system's operation. And finally, you estimate the controllability of the vehicle on that fault occurring and the extent of possible injury to people. Do this a few times for different systems in a vehicle and you have a sliding scale of criticality of a system. This, in a nutshell, is the ACEL classification for systems in a car. The OEM has assigned designed the brakes on this particular car an ACEL D classification, a very critical system, I think you would agree. Now, this classification is for the whole system, and so all the components that contribute to the system inherit the same classification. If SYCL was a component and formed part of the brake system, it would inherit the same classification. Another important principle for ISO 26262 is to have a design reach a safe state. ISO 26262 requires the operational safety analysis to be carried out on a system to identify the conditions when faults may occur and design mechanisms that allow the system to react in a deterministic manner, transferring from normal operational state to a safe operational state. This means stopping normal operations immediately and initiating the transfer to a safe state in a deterministic manner. Transferring to a safe state takes time, and so ISO 26262 has defined the fault tolerant time interval. This is the amount of time from a fault occurring in the system to the hazardous event materializing. Let me show you. A fault occurs somewhere in the system. The undefined system behavior starts to manifest itself to the point the hazard and the injury is very possible. Now ISO 26262 asks that you develop strategies to stop the hazardous event occurring. Whatever strategy is chosen, it must occur in less time than the time the hazard could materialize, and so prevent injury. Think what this means for the SYCL stack. Now, I've mentioned a lot in this presentation so far the word deterministic, and I'm going to mention it a few more times. What is not deterministic about the stack? ISO 26262 asks designers to be able to show they thoroughly understand and can explain every aspect of a system. They like to see models of behavior. The following characteristics of a SYCL stack are neither currently modeled, nor can they be explained satisfactorily. It cannot be shown to be deterministic, and it would be difficult to implement a SYCL stack without most of the mechanisms shown here. I think you would agree. We have dynamic memory, for example. It suffers from latency issues and so shows indeterministic behavior, and this can cause knock-on effects to other parts of the system. However, this could easily be fixed. We also have C++ exception handling. This too is not deterministic because it's not defined by any standard. It's up to the compiler developer's interpretation of how that should be implemented. This again could be fixed. We also have the issue with how kernel execution is managed. How do we manage rogue kernels that do not finish execution? How can we interrupt kernel execution and not enter an indeterministic state? And lastly, and this is very important, wherever in the specification you see the phrase behavior is undetermined, this is a red flag to the ISO 26262 safety standard, and it must be rectified such that the indeterministic is made deterministic. We now have a quick look at a model of what could constitute a SYCL accelerated compute stack for automotive ADAS, sensor fusion or AI applications. It will generally be a vertical system with the hardware at the bottom and the application at the top. We'll start with the SYCL layer and the back-end driver layer, maybe OpenCL, which we're all familiar with. Below that is the hardware device driver, sitting on top of the hardware acceleration SoC. We have the SYCL accelerated application above, which drives the decision making for the critical system. All this would sit alongside a safety certifiable RTOS, and the application at the top is most likely to take inputs from various sensors in the vehicle to assist it in its decision making. Now, errors or malfunctions could appear at any level in this stack. But before I go any further, let me recap. ISO 26262 expects the analysis process to be part of the development of any system. And to ensure this, it's based on a quality management system. It operates as defined in either normal operation or critically reaching a deterministic safe operational state when a fault occurs. The same applies to software components of a system. The OEM determines the ACEL classification for a system and all the components inherit that classification. ISO 26262 expects a design to meet the requirements assigned to it for a particular ACEL classification. And with that, I'm now going to show you some of the requirement tables from part 6 of the standard. There are in all 15 tables like this one, containing in total 90 requirements. I'm going to go through and highlight the ones that I think need some thought and discussion, present a challenge, or on the most part meet quite well. But first let me explain the table. If you see an O in a box, it means the requirement or activity does not need to be carried out. A plus in the box, however, means the requirement is recommended and should be carried out as part of good engineering practice. A double plus means it's mandatory and you must carry that out. However, for any plus or double plus requirement, a deviation is allowed where a wanted case can be made. And with that, back to the contents of this table, Table 1, the modelling and coding guidelines. First up, enforcement of low complexity. This is marked as a concern. This is very much an open question, and some of you will ask, how do you measure complexity in any meaningful way? Well, ISO 26262 is asking for the minimum of code required to satisfy the target use case. Next, use of language subsets. Given this a tick, and I think that this is generally a good characteristic of the SYCL stack as a whole. Use of defensive implementation techniques. This should be straightforward. The checking of data, functions or parameters passed in are acceptable for use. This, however, may draw attention for performance concerns. A tick for well-trusted design principles. I certainly think the design principles like the separation of concerns and promoting clear API boundaries with clear responsibilities is extremely good for the stack. However, concurrency, this is one of the bigger challenges a developer of a SYCL application will have to tackle. This has so many facets it will need handling by the larger SYCL community as a whole. If we cannot sufficiently explain the scheduling of tasks and show deterministic behavior for activities within the stack, this will remain a highly contentious area. Next, Table 3, the principles for software architectural design. A tick here for appropriate hierarchical structure of components. I have put a caution for restricted size and complexity of software components. Now, ISO 26262 is looking for systems and the components within to support only enough code to satisfy the requirements of that targeted use case. A tick for restricted sizes of interfaces. I generally think this is a principle that is well supported. Tricky one, marked as cautionary, strong cohesion within each software component. A good software design principle. This is set the cautionary as this is very much an implementation detail. Linked with strong cohesion is the loose coupling between software components. Again, a good design software principle. The stack as a whole supports this principle very well. Next, the appropriate partial isolation of software components. Now, this could be a challenge depending on how each component is designed and implemented. The standard wants to see evidence that a component cannot interfere and so cause detrimental effects on other components in the stack, which leads us on to the next item, the appropriate management of shared resources. I have marked this as a challenge. ISO 26262 wants to see the stack can operate 24/7 and remain performant and not deteriorate due to poor resource handling. Table 4, methods for verification of software architectural design. There's only one thing in this table I want to bring to your attention, and that is scheduling analysis. This is marked as a challenge, and this particular item complements the other side of the V model, the design and evidence of deterministic scheduling. This requirement asks for evidence that the scheduling within a system can meet a process deadline every time. Moving on, Table 6, Design Principles for Software Unit Design and Implementation. We are now at the bottom of the V model, at the code development call phase. The summary of this table's requirements is to produce good quality code that is free from systematic latent faults. This table in the past, and to a great extent today, is targeted at code bases that are close to the metal, driving the hardware directly. However, this code level requirements brush also applies to modern C++, for better or for worse. Generally, this table does make sense, like the rest of the requirements highlighted in this presentation, but perhaps it's also an indication of how ISO 26262 is lagging behind the necessary modern coding approaches and practices used today. With that, Table 7, Methods for Software Unification. This table is the start of the verification process. You will see the requirements repeat themselves as we move up from the code level to the system integration level on the right-hand side of the V model. Most of the requirements here are again the developer's responsibilities, as they are the component implementers. But I will point out some of the places where the broader SYCL development ecosystem at various levels supports the requirements of the standard. Take, for example, Item 1J, requirements-based testing. A tick, because I think the Kronos CTS is a good foundation on which a developer can use. Item 1K, interface testing, again supported by the Kronos CTS and API specifications. Now, other parts of the stack may present more of a challenge because the requirements are not well defined or validated. An important item in this table is fault injection, and I've marked this as a challenge. I've marked it as a challenge because it's not generally considered as part of the design phase of the stack's development. And yes, you can and should carry out black box testing, but ISO 26262 is looking to see if code within a component is resilient to spontaneous random faults and single points of failure, and that the whole system is not brought crashing down but enter a deterministic, safe operational state. Again, we have a familiar item, resource usage evaluation. Mark this as a challenge, as this accompanies the resource usage item on the left-hand side of the V model. And lastly in this table is back-to-back comparison testing between models and the code. I've highlighted this because ISO 26262 and the automotive industry as a whole base a lot of their work and confirmation of designs using operational behavioral models. They use models to verify all parts of a system and that they operate as they should. If we cannot model a SYCL or OpenCL in their own right, how can we model the SYCL stack as a whole? Moving up the right-hand side of the V model, methods for deriving test cases and software unit integration. We'll have a quick look at this table just to highlight item 1C, the testing of values approaching and crossing the boundaries of out-of-range values. I've marked this as a challenge as currently the Chronos CTS for both SYCL and the OpenCL specifications either do not carry out negative testing or it is a bit on the light side. Whether it is partially enabled by the Chronos CTS specifications or not, it is ultimately the responsibility of the developer to carry out negative testing when and where appropriate. This is the second to last table in this presentation on its methods for the verification of software integration. The requirement to be considered in this particular table is item 1F, the testing of the integrity of data that would move between components in the stack. This can include the checking the amount of data that is expected is within range, not too small, not too large, and that the system could not unexpectedly churn. On the point of churn, the system may not have gone wrong, it's operating as expected, but it's been given data of a size that is unexpectedly large in size. And while this is not specifically a requirement of ISO 26262, restricting and checking for the tampering of data is asked for by the cybersecurity guideline SAJ 3061. And for example, that could be a denial of service attack. Okay, we finally reached the last table, but this is quite an important table, and I highlight here item 1F and I've marked it as a challenge. The analysis of use cases for embedded software. Generally for automotive safety software, the standard and the OEMs require the system to be able to perform self-tests periodically, which means as part of the use case and as part of the defined functionality, the stack may be required to perform regular self-tests to ensure all systems are operating within defined parameters. As part of one or more types of self-tests, it is very likely that hardware and sensors will be included in these tests. The important point to note here is they're performed on a defined regular basis, which may mean the application needs to time slice the test to fit in with normal operation or interrupt itself. If there is time within a cycle, this shouldn't be a problem. But if we're cutting it close to the mark, there's not enough time, then the stack have to be forced interrupt. And this could be problematic in the middle of the execution of kernel, for example. That concludes my presentation. I don't think it's all doom and gloom. It just means we have some work to do. SYCL and OpenCL were not designed with safety in mind. All of the implementations to date are not targeted for the safety market, and therefore there will be challenges. I think you would agree a SYCL accelerated stack is a very viable proposition for critical systems in a vehicle. However, the onus is on the safety as the ACEL classification goes up. Taken as a holistic approach, as we have done here, it does show that the SYCL stack does already have some good design principles, supported by solid requirements and specifications from Chronos. Now, the devil is in the detail, and it will be the individual component implementers that will need to do most of the work. But there's also a broader, joined-up, concerted effort by the industry bodies like the C++ ISO committee, coding implementation quality standards like MISRA and OEMs themselves. But there is good news. There is evidence of this cooperation already. The improvements required for safety applications listed here start at the implementation, design and code coalface level, but need the support of a well-structured framework to hang safety strategies from, and the cooperation of the parties which have been mentioned already. Some of the issues are very complex, and this will take time to develop the thorough understanding and evidence, and followed by the work needed in updating the safety standards to complement the complex systems of tomorrow. This would go a long way to giving assurances the OEMs want and ultimately lead to SYCL-powered systems in vehicles. Sure, these problems are not just limited to SYCL stack, but other competing highly parallel systems like NVIDIA's CUDA, they have to do all the same work too. An important point to make here is ISO 262 wants all the players in all parts of the stack to be responsible not only for the safety of their constituent parts, but be responsible for the immediate parts connected to their parts, which in turn leads to the whole system. All ISO 26262 is asking for at the end of the day is evidence of good engineering practices backed up with a verification and validation plans to show a product can operate safely even when it develops a fault. The SYCL powered stack is a viable alternative for the automotive industry's OEMs, and they're very interested. It is attractive in many ways, including it gives the OEMs options in their manufacturing and not be tied to any one vendor. The SYCL stack scorecard is okay average and has some good characteristics but could do better in places. And there is the final challenge which I have not mentioned yet. Can you be involved in the development of a SYCL application stack for safety for the long haul, tens of years, as this is the expected lifetime of the vehicle? and so you have to keep it maintained. Takeaway point from this presentation is the SYCL stack needs to be deterministic. It needs safety mechanisms, yet still remain performant. With that, I will leave you with the fact that someone might come up with a witty comment to put on a t-shirt about deterministic behavior. That's it. If you have any comments or questions, my email is on this last slide. Thank you.